Next, we'll work example 6.10, partial pressures and mole fractions. A 12.5 liter scuba diving tank contains a heliox mixture made up of 24.2 grams of helium and 4.32 grams of oxygen at 298 Kelvin. Calculate the mole fraction and partial pressure of each component in the mixture and the total pressure of the mixture. We learned that the partial pressure of a component is equal to the moles of that component divided by the total pressure, and the total pressure can be calculated by the total moles times RT over V, and we know that the partial pressure of a component can be calculated as the mole fraction of that component times the total pressure. Well, we weren't given the moles of each component, but we were given the masses and the identities of those components. So from those masses, we can calculate the moles of each component, and we can use the volume and the temperature to calculate the total pressure. So we'll use the mass to calculate the moles of helium, the mass to calculate the moles of oxygen. When we have the moles, we can calculate the mole fraction of each component as the moles divided by the total moles, or the moles of oxygen divided by the total moles. So that gives us the mole fraction. And then our total pressure will be equal to the total moles times RT over V, and T and V were given. Next, we can calculate the partial pressure of each component from the equation, the mole fraction times the total pressure. Okay? So here we have 24.2 grams of helium, and we use the periodic table to convert grams to moles. So if you look at the periodic table for helium, helium is over here. It's 4.003 grams per mole, and that gives us 6.05 moles of helium. Then we can calculate the moles of oxygen, 4.32 grams of oxygen. Oxygen is a diatomic molecule, and the atomic weight is 16, so 16 times 2 is 32 grams per mole. That gives us 0.135 moles of oxygen. Next, we can calculate the mole fraction of each component. The mole fraction of helium is equal to the moles of helium divided by the total moles. Now, you could put those in separately, or you could just calculate the total moles, which is 0.740, and put that here. So that's equal to 6.05 divided by the total moles, which is 0.97817. The mole fraction of oxygen is equal to the moles of oxygen divided by the total moles, which is 0.135 divided by the total moles, which is 0.021827. Now, the total pressure can be calculated from the total moles times RT over V, which is equal to this number here times R times T divided by V, and we get 12.099 atmospheres. That's the total pressure. And we learned that we can calculate the partial pressure by the mole fraction times the total pressure, which is equal to 0.967817 times 12.099 atmospheres for helium, which gives us 11.8 atmospheres of helium, and a partial pressure of oxygen of the mole fraction of oxygen times the total pressure, which is 0.021827, times 12.099, which gives us 0.264 atmospheres for the partial pressure of oxygen. Now let's work a for-practice problem, for practice 6.10. Okay? A diver breathes a heliox mixture with an oxygen mole fraction of 0.050. What must the total pressure be for the partial pressure of oxygen to be 0.21 atmospheres? All right, so we know the mole fraction of oxygen is equal to 0.050, and the partial pressure of oxygen is equal to 0.21 atmospheres. We know the partial pressure of oxygen would be equal to the mole fraction of oxygen times the total pressure. Okay? So the total pressure would be equal to the partial pressure of oxygen divided by the mole fraction of oxygen, which is equal to 0.21 atmospheres divided by 0.050, okay, which is equal to 4.32 2 atmospheres.